Next up, we have Patrick McClurg, who will be speaking about how to achieve truly random outcomes using DRAND. Patrick, everyone.
Good afternoon, Oracle nerds. I'm Patrick. I'm from the DRAND team inside Protocol Labs. You may have heard of Protocol Labs from IPFS or Filecoin or libp2p fame, but there are yet more good projects that we've developed, such as DRAND, which I'll be shilling toward the end of the presentation today. So first off, what is randomness? Well, there's lots of fancy academic definitions of that, but for this presentation, we'll just assume it's choosing a number from a range which nobody can guess at a rate better than chance. OK, so what can you use it for? You're probably all pretty familiar with randomness here, but here's some example use cases. For instance, your Bitcoin private key is essentially a big random number. Anytime, if any of you people have done the lottery, the dude with the white glove who selects the balls from the weird machine that spins around and around, that's essentially selecting random numbers. In the top left, we've got Magic the Gathering, a legal drug that strips nerds from money all over the world. Shuffling a deck is, in essence, coming up with a random permutation. Selecting people for jury duty is another example of using randomness. And some of the keen-brained among you may have noticed some of these applications are not quite like the others. In essence, some of them use public randomness and some use private randomness. So for example, Bitcoin, you probably don't want to tell anybody your Bitcoin private key because they're going to steal all your Bitcoin. But obviously, if you used private randomness to select jury duty, then it could be biasable and people might pick the same people every time. So that kind of leads nicely into one of the problems, difficulties with doing randomness on chain is on the blockchain, everything's public. It's also deterministic. So in the deterministic sense, computers are by nature deterministic. So it's quite hard for them to come up with random numbers in that it's not very random if everybody can just do the computation themselves. So we need to find some method of achieving randomness on the blockchain that can't be influenced by others and also can't be predicted by others, or you're not going to have very good lotteries, for example. So looking back to some of the early days of blockchain, when it was just coming out and we didn't have lots of fancy oracles and other tech, a lot of people used block headers as a random value. And for low-value use cases, maybe some tenet of a game, for example, that might be good enough. But the issue with block headers is, of course, that they're biasable. You can imagine if we had a lottery that was worth millions and millions of dollars, miners may choose to include or not include certain transactions in a block to try and influence the value of the block header so that they could potentially win the lottery or make sure certain people don't win the lottery. So, we've come past that stage, but that was something some people used in the past and probably not good if you're doing anything important. So the next stage along in Ethereum land, at least, was to create Randa, which you may have heard of. It's kind of the go-to source of randomness native to the Ethereum blockchain. And as a quick refresher for anybody who doesn't know how Randau works. Essentially, we've got 128 slots rather, in a smart contract, and people with a stake can provide some entropy into this contract. And in fact, it happens in two phases. First, they commit to some piece of entropy by providing a hash of that, and then at some later phase, they reveal or choose not to reveal their entropy. And all those bits of entropy are combined together into some final random number. So that sounds pretty good. It sounds like, you've got 128 people. It sounds pretty random. But the issue is, it's biasable. In essence, if you're someone with a lot of stake in the Ethereum network and you manage to get a whole bunch of these slots, particularly at the end, you could choose to reveal or not reveal your committed randomness in order to influence the final result. And each slot adds up to around a 1-bit bias on the output number. So again, depending on the value of your use case, this might still be enough. Like, if someone like Coinbase, who owns lots of slots in Randau, want to, try and, win your fancy sword NFT in your game, that's probably not worth their time. But equally, if you've got a lottery worth bazillions of Ethereum, then maybe it is worth their time and they might pwn you. But we moved on from RANDAO, and of course this is an Oracle conference after all, so we've got fancy oracles for this. So you could use a VRF. For legal reasons, I've just included a picture of a chain link fence here. Not referring to any specific VRF here, but okay, so VRF's a little bit better here. Now it's not biasable in the same way that RANDAO is biasable. They've published lots of fancy algorithms about how it works. And you can dive into the details, get a cryptographer to look at it, and all looks pretty good. However, it's got a couple of issues. The first is, well, it has single-party trust assumptions. I mean, if you're using unnamed VRF Oracle for certain blockchains, you're kind of relying first that they developed it correctly, secondly that the details they've released on it are correct, thirdly your PhD galaxy brain that you've hired to look into the details has correctly read it and it actually works as you expect it, which that's a lot of assumptions, which again might be good for your use case, but could also be scary. Additionally, it can be quite expensive. So if you have to do lots and lots of logic in your callback for certain VRFs, you get charged a percentage of the gas fee. So if you're doing loads of computations, it's going to be very expensive for every random call. And yeah, maybe if you're handling billions of dollars, maybe that's a small fee, a small price you're willing to pay. But we can do better. Another possible route for randomness is using threshold cryptography. For those of you not familiar with threshold cryptography, it's in essence taking a public and private key pair, but splitting the private key into a whole bunch of mini private keys or partial private keys and distributing them amongst a bunch of different people. Those people then have to come together and work cooperatively to act on behalf of the private key. So, for example, if we have n participants, we need to cross some threshold number of those working together in order to output a signature that is valid for that public key. The cool thing about threshold crypto is that no single party ever has the private key in memory. So if we wanted to create randomness, we can sign a message, and because nobody has access to the private key, they can't anticipate what the signature is going to be over some message, and therefore it's indistinguishable from randomness. So, ooh, now we're talking. As a side note, threshold cryptography, very cool for some of the other things we've talked about today, like data provenance, for example. We could give some data to a whole bunch of people and get them to sign it, and we can, that gives us a bit more spread trust on that someone has actually seen the data and verified its validity. And now for the shield part of my presentation, ooh, a wild DRAND appears. So what is DRAND? Well, it's a threshold network for generating publicly verifiable, unbiasable, unpredictable random numbers. I've gone into the threshold aspect of that a little bit already. We've discussed publicly verifiable is super useful on chain, and because the random number is in essence a signature, we can use all the usual suspects for verifying signatures that we're all used to, rather than having to rely on some hard to figure out VRF. A sort of confusing part of the threshold signature idea is that, in fact, all the random numbers from here until the end of time are already deterministically decided once you generate the key. So in that regard, it's unbiasable. Even malicious nodes can't create a valid signature that will turn into some valid randomness. But because, again, nobody has the private key, it's unpredictable. So DRAND signs a message every epoch using some fancy maths. Those DRAND epochs map to a precise time on the clock, which means that we know the message in advance that the network is going to sign, which enables some other cool things that I'll talk about in just a moment. And right now, DRAND emits randomness every 30 seconds. We've actually just launched a new network that emits randomness every 3 seconds, so that could be good for some specific gaming use cases. And coming back to quashing the single-party trust assumptions of some other randomness models, DRAND is run by a non-profit consortium called the League of Entropy, which consists of 16 organizations, some of which you may have heard of, such as Cloudflare, Also, a lot of universities like EPFL, UCL, University of Chile. There's some Web 2 companies, there's some Web 3 companies, Protocol Labs, they're great. Ethereum Foundation. And the crux is that as long as there are never a threshold number of malicious nodes in the network, you can trust that everything is above board and legitimate. And compromising a threshold number of very different, geographically distributed parties would be quite challenging. I said a moment ago that it enables something else that's very cool called time lock encryption. Essentially, the ability to encrypt something now that can't be decrypted until some future time has passed. Although that's outside the scope of this talk, but if you want to try it, I've got a QR code for you to scan, which I'll give you 10 seconds here to get your phone out and do the business. There's a paper and libraries and all manner of other cool things that you can read up on time lock encryption there. So finally, I guess some asks for you. Let's collaborate. I think threshold cryptography has a lot of cool applications in the Oracle space. In particular, DRAM right now isn't on a lot of chains, so it's available in the Cosmos ecosystem thanks to the Noise Network, who are also an Oracle provider, specifically for randomness. It's available in the Filecoin virtual machine. It was available on Terra, but unfortunately, not anymore. It's kind of available on Ethereum, but unfortunately, BLS 12381, i.e. the threshold signature scheme we use, the operations for that are not native to Ethereum, and they're very, very expensive in gas cost. So if you can shield this EIP in the bottom right to get them accepted into Ethereum mainnet, not only will you enable DRAM verification on Ethereum, but also all the cool Oracle use cases using threshold cryptography will become available to all of us. Also, if you've got some infrastructure, you could join the League of Entropy as well. We're always looking for new members, as long as you can run a production-grade infrastructure and your servers won't fall over. Yeah, that is everything I've got. Here's some cool links as well, and I'm open to any questions from the floor that you might have on DRAM or threshold cryptography.